Dear student, I am Dr. Harel Thomas, Professor in Applied Geology, Dr. Harisingh, Gour, Vishwavidyalaya, Sagar. Today, I will deliver my lecture on parent composition of metamorphic rocks. In this lecture, I will proceed under the following heads: bulk composition and summary. Hope it will be useful for you. Try to be regular in course. Bulk composition play an important role during metamorphism because the bulk composition is responsible for the formation of new metamorphic rocks. For example, if peltic rocks, the parent rock must be argillaceous in nature, where SiO2, Al2O3, K2O, Na2O, CaO, FeO, MgO are responsible major oxide which can give rise to schist, gneiss or phyllite, etc. after metamorphism. For this, mudstone or argillaceous rock must be a parent rock. Similarly, for the quartzite SiO2, the original rock type is a sedimentary orthoquartzite, always act as a source rock. Metamorphic rocks are derived from sedimentary, igneous and already metamorphosed rocks. It is obvious that the chemistry and mineralogy of the parent rocks called protolith control the composition and to a large extent also the mineral association of the metamorphic rocks. Metamorphic process is strictly isochemical and the volatiles H2O, CO2, etc. may not alter the bulk rock chemistry. The volatiles being in equilibrium with the minerals in reactions and hence free to enter or leave the rock system are unable to alter the bulk rock chemistry of the metamorphic rocks. It means that the parent mineral assemblages retain the parent chemical composition of the metamorphic rock. Based on chemical consideration, there are 5 types of parent compositions for metamorphic rocks in approximate order of increasing grade. Most common peltic or argillaceous composition is the shell or mud rock and hence rich in clay minerals. Chemically, these rocks are Al rich but contain significant amount of silica and minor alkalis, iron and magnesium. The peltic composition is most sensitive to small temperature difference and these rocks are called metapelites, and metapelites are very useful in studying temperature and pressure variation during metamorphism. In the initial stage, the metapelites are fine grained with excellent rock cleavage is called slate. Continued metamorphism increases grain size and produce the rocks phyllite, schist and gneisses. Characteristic minerals in the schist are micas, garnet, stolite, kyanite, sillimanite, and cordierite in various combinations. Rocks under this category are sandstone, arkose, or granitic types, which constitutes predominantly of quartz and feldspar, are normally composed by SiO2, Al2O3, CaO, K2O, Na2O, S2O. Gneisses derived from granite family, for example, deformed granite, also come in this category or in this group. Metamorphism of this composition does not produce a wide variety of minerals, and the common association is quartz, feldspar, plagioclase, and alkali feldspar, micas, but at the higher grade one may find garnet or cordierite, sillimanite, and even hypersthene. The carbonate rocks, limestone, and dolomites are common and dominantly contain calcite and dolomite with minor silica and clay fractions. At low temperature, the non-carbonate minerals are dominated by hydrous species such as chlorite, phlogopite, talc, or tremolite, which are replaced at high temperature by anhydrous minerals like diopside, forsterite, wollastonite, gracilorite, and calcite, plagioclase, etc. More common than marbles are the calcilicate rocks, which are impure carbonates or marls, calcareous cells. A medium to high grade calcilicate resembles amphibolite, a metamorphosed basic rocks. Characteristic low grade calcilicate minerals are chlorite, epidote, and actinolite. At higher grades, these are replaced by diopside, hornblende, gracilorite, and calcic plagioclase. The basic protoliths are the andesites and basalts or gabbros. Low grade metamorphism of these rocks produces green schist or greenstones, which are characterized by chlorite, epidote, actinolite, and sodic plagioclase, albite, anorthite less than 7%. At higher grades, the greenstone is changed into basalt, which is made up of hornblende plus plagioclase pair, sometimes with garnet. At highest grade, more than 700 degrees centigrade, even hornblende becomes unstable and is replaced by clinopyroxene, orthopyroxene, and plagioclase. The mineralogy of the highest grade mafic rocks begin to resemble the original mafic protolith mineralogy, and a distinction is possible on the presence or absence of metamorphic textures. Usually, the basic rocks contain SiO2, Al2O3, MgO, FeO, CaO, Na2O, S2O, plus minus CO2. The ultramafic igneous rocks usually contain SiO2, MgO, FeO, CaO, S2O, plus minus Al2O3. The rocks which are formed, that is ultramafic, petrotite, etc. Metamorphic rocks and Mg rich sediments. At low grade, these compositions form talc, serpentine minerals, orthoamphiboles, anthophilites, or clinoamphiboles, cummingtonite. At high grade, the minerals are pyroxenes, olivine, garnet, and spinel, and minor plagioclase. A special class of rock is iron formation and ironstone. These are magnetite-rich quartzite. At low grade, this composition contain iron-rich mineral such as iron serpentine, iron talc, and iron-rich amphiboles, ferroactinolite, ferrocummingtonite, and grunites. High-grade assemblages contain magnetite, fayalite, iron-rich pyroxene, heidelbergite, and almandine garnet. Weathered and oxidized occurrences may be hematite-rich, iron-rich, metamorphic lithologies are found in Middle Precambrian period. Dear student, today in this lecture, we have discussed about the parent composition of metamorphic rocks. I have covered this topic under the following heads: bulk composition and summary. I believe this lecture was useful for you. For further studies, please read the textbooks, references and links given in the text. Thank you very much.